Oh yeah, that's right. I forgot. I have to be wired. Is this okay up there, somewhere like that? Okay. Working? All right. And then I got my little thingy. Okay. And I'll just introduce myself. Oh, shoot. Okay. Good morning, everybody. Can you hear me if I leave it on the podium here? I know most of you, I think. If I don't know you, I'm Carrie Earthman, and I have the pleasure of being here to talk with you about amino acid metabolism. And Dr. Chen is always graciously allowing me to do this because it's something that I like to do. I used to teach metabolism back at Virginia Tech, and it's just something that is, near and dear to my heart. So we're going to talk about a few different things over the next 2.5 days, I guess, in class with you. I'm sorry, I feel low energy, and I've got this horrible throat, so I sound like a frog, and, it just makes my low voice even lower, which is not ideal at this time. Well, it's not that early, but anyway, it does feel like it's a bit... So bear with me, and if you can't hear me, if I start to just, get lower and lower, and raise your hand and tell me to wake up. So we're going to start with if I can get this to go. Oh, you know what? It's helpful if you put batteries in these things. Okay, I'm going to use the old-fashioned way here for a minute. Actually, maybe I can get Shelley. Would you mind helping me? I'm not sure which ones. Thank you. Okay. So we're going to start with this is a review. I'm certain that you have had, the basics of protein chemistry, at least, through biochem and all that. So bear with me a little bit as we, thank you so much. And then I think we hit the button. There we go. All right. So protein structure, as you may be aware, has some very cool structures. Proteins are very unique. Each protein is unique. It's got different levels of structure that allow them to come together in 3D that look kind of cool. So this is just a picture that I think is interesting. And then very much a review, the general formula for a protein. You've got chains of amino acids in sequence in the primary. They're held together by peptide bonds, right? I'm sure this is a review. And we've got basic structures, the primary, secondary, tertiary, and quaternary, right? It's all coming flooding back from biochem, I imagine, by now. Also very basic. Amino acids are the building blocks of proteins, right? And we're going to talk about what makes each amino acid unique as it's R group. That'll be a little bit from now. But we've got an alpha carboxyl and an alpha amino group that you just need to just remember those as we start talking about proteins and how they come together in sequence. So amino acids come together to form peptide bonds together, right? And so we got the carboxyl group of one amino acid combining with the amino group of another amino acid, come together by a peptide bond, and that's a dehydration reaction. So we end up with this peptide bond, water is produced in it, and now we have a dipeptide, right? This is just a quick reminder in short form of the 4 levels, okay? We talked about primary sequence, that's peptide bonds connecting amino acids in sequence. Remember secondary level structure where it's hydrogen bonding that keeps that together. And we've got beta-pleated sheet or alpha helix as the structure options for that. And then tertiary is how you get interactions from amino acids that may be quite far away from each other in the primary sequence, but they come together like hydrophobic interactions and disulfide bonds and various other types of interactions that help the protein fold up and make its globular structure, sometimes globular or other. And then quaternary is when you have multiple peptide chains. I am getting low. I can feel it. Raw, ribbit. Sorry. Okay, so we've gone over primary. This is a tripeptide. I'm just highlighting that every time you see a different R group, that's designating that it's amino acids. Here's a beta-pleated sheet where you got hydrogen bonding bringing it together to folds. Here's tertiary structure, and I just labeled this. This is an alpha helix at the secondary structure, and then it folds up to make its tertiary structure. What else do I want to say about that? And, well, let me just back up. So the tertiary structure, remember, you've got, we talked about hydrophobic interactions. I mentioned disulfide bonds. Are there any other kind of interactions that you remember that help a protein fold up to keep its structure? Other than that, what, van der Waals? Yeah, great. Who said that? I'm trying to, thank you. Any other? Positive and negative charge? Yeah, ionic, right? So electrostatic or ionic. And those become really important when we talk about pH of the stomach and other pH issues. Okay, and then quaternary structure. Hemoglobin has 4 chains, 2 alpha, 2 beta, and it allows it to fold up to make its unique structure. So, okay. Now, this is a roadmap that we're going to loosely use as we move through amino acid and protein metabolism. And I guess next I want to talk about, this is exciting, so yeah, okay, woohoo. We're going to talk about protein digestion and absorption, and this is also very basic, back to physiology. But a couple of points I want to make while we're here is that we've got 2 primary sources of protein, right, that get presented to the GI tract. Exogenous, what we eat, and then endogenous, and there are a whole lot of sources of endogenous, including, you know, sloughed cells, digestive secretions, and other things like that. And the other point that I like to make here is that we're really efficient. We don't lose very much nitrogen. So this is just to give it some proportionality. You know, say we take in 100 grams of protein through our diet, 70 grams are coming in endogenously through you know, the sloughed cells and digestive secretions. Only about 10 grams goes out as undigested fecal nitrogen. So we're really pretty darn efficient. And the rest enter the amino acid pool. We'll talk about that soon, but let's just talk a little bit. I'll stay here for a moment. Just over here, we've got some other nitrogen that gets lost from the body, right? So remembering physiology again, integumental losses. That's, you know, skin, sweat, hair, you know, other forms of nitrogen that can go out. And I guess I'll say it here. The other thing that we do is we recycle nitrogen from the colon. And we do that as urea. So we can absorb a fair amount of nitrogen at the colon. We don't absorb amino acids at the colon, right? But it's just recycling through urease activity, through bacteria that break down urea that ends up in the colon, and we can kind of recapture some of that nitrogen there. Okay, brief review of digestion. So you're going to have to help me with this, right? So hopefully you'll remember the basics. So protein digestion, right? It involves a healthy stomach, small intestine, and pancreas for it to happen efficiently, right? So it begins at the stomach. What do you remember about HCl, right? So the stomach, we have hormone gastrin that promotes HCl release in the stomach. What is the hydrochloric acid or the acid doing for protein digestion? Did I hear something? Okay, what is it doing? It's denaturing the protein. Okay. What do we mean by that when we say denaturing the protein? Okay. Unwinding. How does it do that? Not. Absolutely great that you said that, Amanda, but that's not, okay? So what the HCl does not do, and this is on the exam, you know, it does not break peptide bonds. It does not do diddly squat to peptide bonds, right? But it does denature the protein. So what's it doing? How's it doing that? Yeah, that's correct. It's creating an environment where those bonds can be broken down. Yeah. So that's a big one, right? It's interrupting the ionic bonding. It's changing, and we're going to talk about how that happens. So it's interrupting the structures, hydrogen bonding as well, but those ionic bonds are really important for keeping a protein together. And what you just said is right? It unfolds it so that it allows the enzymes to get in there. Does it do anything else that you remember? It's like, dredge back to, I don't know, what basic class was it? Advanced Human? Where did you learn this? It's been a while. Beautiful. It activates pepsinogen to pepsin, activates pepsin, right? Converts pepsinogen to pepsin in the stomach. And that's our first really important peptidase. And that acts on the peptide bonds, right? So the acid is absolutely, pretty darn important for unfolding the proteins and beginning to allow that access, and for activating pepsin so that we can start breaking those peptide bonds. Incidentally, and this is not related to protein, the pH of the stomach is also important because it kills things coming from, bacteria that are coming in with our food, potentially state fair food or, other things like that. That's not really related to protein metabolism. Okay, so we've got the second answer, right? Pepsin is starting to break down proteins, breaking those peptide bonds. All right, so we're leaving the stomach now, right? So the stomach, you start to get some macro molecule. Protein, you get large polypeptides, some free amino acids, but mostly we got large polypeptides and oligopeptides as a result of pepsin in that environment of acid. And then we get to the small intestine, and the duodenum is the first part where we are, and over the whole small intestine, proteins get completely digested. And we have both intestinal and pancreatic enzymes that are working, right? Proteases, they attack the peptide bonds. And do you remember the terms exo and endopeptidase? What's an exopeptidase? Do you remember that from biochem? That might have been. It just means it's cleaving the amino acids from one at a time, from the end, one end or the other, okay? Whereas endopeptidases act in the interior of the sequence of amino acids. So we've got the primary sequence, and endopeptidases will work on, typically they're specific for certain residues, so whenever they see a glutamine or whatever, they'll chop it or that kind of thing, rather than just from the end. Okay, now you don't have this, but I just want to remind us that we've got acid chyme coming from the stomach, we're hitting the duodenum, the pancreas is critical in what we're going to see next in this next slide, right? So we've got entry into the duodenum of acid chyme containing these protein remnants and small peptide kind of things. And those are stimulating, that acid chyme stimulates the intestinal endocrine cell to release CCK and secretin. I've just written out cholecystokinin for you in case you've forgotten what that CCK stands for. And then CCK and secretin are having kind of dual action. They act on the pancreas over here, and they're also acting on intestinal mucosal epithelial cells. Their action in terms of the intestinal mucosal, these cells, is to release enteropeptidase, which is a really critical enzyme. And I'm animated here, so we'll move up first to what the effect of the CCK and secretin are on the pancreas, if you are not remembering, right? So the pancreas will release trypsinogen, a proenzyme, and at the same time it's also releasing bicarbonate, right? And anybody remember what the purpose of the bicarb is, the bicarbonate? What important role does that have in digestion, coming from the pancreas into the intestine? Sorry? Okay, yep. So as it's neutralizing that acid chyme, it's bringing the pH up, right? What importance does that have for protein digestion, do you suppose? Okay, so it's creating the environment where the enzymes are going to be optimally active, right, by increasing the pH, because we know that all enzymes have a sweet spot for the pH, right? So that's important. The trypsinogen, it is activated to trypsin by enteropeptidase. So without enteropeptidase, you're not going to get activation of trypsin. And so trypsin is kind of the band leader for the pancreatic proenzymes. Once you get trypsin made, it will auto-catalyze more conversion of trypsinogen to trypsin, but it also activates chymotrypsinogen, proelastase, and procarboxypeptidase to their active form. So these are all pancreatic enzymes that are really require that coordination of effort between the intestinal endocrine release of CCK and secretin to get those activated. Okay, so we've got the bicarb coming from the pancreas. So we begin to think about this in MNT anyway. In maybe a week or two, we're going to talk about pancreatic disorders, right? And so if you think about protein digestion, adequate protein digestion requires a normal functioning stomach, but it's essential that you have an adequate, a functioning pancreas as well. And if you don't, you've got pancreatic insufficiency, you're going to have compromised ability to digest protein as well as fat and other nutrients, right? So that's why I go over that. Okay. What next? So we're in this is my beautiful picture of a, here we are in the intestinal, the lumen here, right here. And we've got pancreatic and intestinal enzymes that are working on these, right? That's where we are in the duodenum. And then we've got absorption happening, right? So here we are in the absorption, and we can absorb small peptides as well as free amino acids, and then once they get into the enterocyte, we have small peptidases, intracellular peptidases that can act to further break down the peptides. We also know that we can absorb small peptides. So we have some bioactive peptides that a lot of people like Pam Ishmael and others in the department have been, investigating these bioactive peptides that maybe have antihypertensive qualities, or they have some appetite regulating qualities and that kind of thing. And, oops, so hold on, I think I have another diagram, so we'll continue here. So those small peptides and free amino acids come across the brush border by active transporters. Okay, so the main or first point I'd like to make is that there are separate absorption mechanisms for small peptides and free amino acids, and there are specific ones for various amino acids and small peptides. The other thing is that small peptides are really kind of the predominant way that we bring in, or the most efficient way that we bring in amino acids across the gut for absorption. So the small peptide carriers are very efficient, and right, so different sets of transporters, and I'm trying to think what other point I wanted to make here. And then across into the blood, through that basolateral membrane, we've got diffusion of free amino acids, and this is where I needed to say this here about small peptides, sorry, is that we'll have some small peptides that also can cross the basolateral membrane into circulation. Okay, so that was, I said that a bit early. So this is where it happens. We get those bioactive peptides, some of them that can come from whey protein and soy protein and other forms of protein that can cross into the bloodstream, okay? Yeah, good enough, I guess, for now. And then we're going to end up, those amino acids are going to go to the liver, where we're going to talk a lot about what happens to amino acids at the liver in a bit here. So basic principles about amino acid transport. There's redundancy, right? You may remember this. Redundancy meaning there are one amino acid may be transported by several different transporters, right? There's competition. So amino acids for one carrier will compete with each other, can compete with each other, right? And there's a lot of overlap. The other thing is each tissue has a unique set of a unique set of transporters that will facilitate it getting what it needs. Right? So each tissue has its own complement. And then transporter activity can be affected by hormones and physiologic state. And I give you the best example that I can think of is glucagon increases the A transporter that carries alanine in liver cells. So can somebody explain to me why that would be? Yeah. It has everything to do with that, absolutely, right? So that makes sense, right? That's a good thing that we can do that, right? So we'll bring more alanine in under conditions when we need to be making glucose, gluconeogenesis, alanine being really our primary or great precursor under fasting conditions particularly, right? Okay, so amino acid absorption characteristics of amino acids. Oh, so other things about absorption. Amino acid, they can vary in terms of how fast or efficiently they're absorbed. So we know that essential amino acids, or the non-dispensable ones, tend to be absorbed faster than the non-essential ones. We also know that large amino acids tend to be absorbed a little faster than smaller ones. And many of our larger ones are the essential ones too, so that may be partly related. We know that there's competition between amino acids for the same carrier. If you've got one that uses, a couple of amino acids that use the same carrier. So I want you to just think about, what about people that are taking amino acid supplements? Maybe they're taking leucine or, one particular amino acid, or maybe a couple amino acid supplements. Based on what we know about amino acid absorption, what would you say to somebody that says, should I be taking, an amino acid supplement? What would you say? Anybody ever ask you that? I don't know, travel on an airplane and tell somebody that you're a nutrition person, you might get asked these kind of questions. Come on, help me out here. Willie? So that's a great answer for that, right? And so specifically, if somebody were asking about supplementing one or two, okay, not a whole protein, but they're talking about, the thing that people do. They take branched chain amino acids, or they take leucine. What would you say, based on what we know about amino acid absorption? It's excellent, right? It's certainly likely that you're going to get the competition going, depending on which amino acids there are. You quite likely could be counterproductive, right? And in fact, we don't see positive impact of this when it's one or two, because of the fact that you're not optimizing absorption, for one thing, because you're causing competition between amino acids based on what we know about amino acid absorption. The other thing is that we also know that there are different mechanisms, and small peptides tend to be absorbed more efficiently and faster. You're better off eating whole protein, and we don't really need as much protein as people tend to think, right? Because we already have a pretty high protein diet if we're eating a Western style diet. So most people are pretty, it's not a necessity at all, very likely counterproductive, and certainly expensive, and doesn't taste very good. So there are lots of reasons why you would not want to support your GNC, by going to buy these particular amino acid, supplementation strategies. Yeah. Yep, and I'm going to say even that, it's the same rules apply. So if you're just taking glutamine, you know, and in part, clinically speaking, we have not, you know, theoretically it sounds really good to take, and I'm getting ahead of myself, but glutamine, you know, has been looked at because under certain conditions where we have metabolic stress, you know, and I'll talk about this way at the end if I get there, not today. You know, we think, well, that could be beneficial because, you know, blood levels drop, and glutamine is thought to be conditionally essential in metabolic stress. And what we found is that supplementing with glutamine, actually there are some powerful negative effects in people that have sepsis, for example, you know, systemic infection. And I'm not going to have time to talk about it in this class too much, but I will in M&T a little bit. So it's something that we know that you've got competition regardless of what amino acid it is, right? So I think that could very well be part of it. There's also some other metabolic things going on by that your body may be, you know, there may be some reasons. Always there's a physiologic reason why one particular nutrient will fall or under certain conditions. So we'll leave that there. But anyway, for now, just again trying to apply the principles of what we understand about the physiology. It can be helpful as you move forward in your careers as nutritionists and/or wherever you end up working as dietitians or doctors or whatever. So on that note, I always, you know, this is my opportunity to, you know, kind of get the M&T people razzed up, you know. But if you think about what we just talked about, if you have pancreatic insufficiency, right, so the pancreas isn't working so well, the kind of tube feeding formula, what you know, and so people that are in M&T, you already know some of this. So if there are people that are not in M&T that maybe think about what we could do, what might we do to a formula that we're trying to feed somebody to meet all of their needs when they may have pancreatic insufficiency. The pancreas isn't working very well, right? Which specifically about protein, what can we do you suppose? And maybe I need somebody from M&T to, you know, pipe up if there aren't any other ideas. Yeah. Okay. So we wouldn't necessarily, the way you've said it, right? So if you were in a food company and you were making a formula, what would you do? You would take protein, right, and then you would treat it to create a hydrolyzed form, right? So that the idea of amino acids, but not just free amino acids, right? Why not? Why not just hydrolyze the heck out of it and it's all in the form of free amino acids? Tell me why that would not be the best way to go, based on what we've just talked about this morning. Yeah. Oh, Sarah, or right. Small peptides are absorbed better, right? So we don't want to just give free amino acids, but we do want to hydrolyze the protein so that we can optimize the efficiency of absorption. So if we do a partial hydrolysis, food scientists that might be in the room, right? Partial hydrolysis means we're going to have some small peptides, we'll have some free amino acids, and we'll take advantage of the dual absorption mechanisms and optimize absorption of that protein in that formula. Now, incidentally, we also tend to do something to the fat content because pancreatic insufficiency also you have fat malabsorption, but that's for another day. But for protein, that's the primary thing that we're going to be thinking about is small peptides and free amino acids that can help assimilate that protein. Okay, any questions about that? Digestion, absorption. Okay, so those of you that end up working at supplement companies, you know, like Abbott, some of you will. You might work, even Hormel was developing a bariatric formula a while back. Or other companies, other food companies will be, you know, thinking about these sorts of things. So I want you to remember these principles as you go forward so that you can help them, you know, do that better and meet our needs in the clinical setting. All right. So if no questions on that we'll move on to protein requirements, which again is also a bit of a review. And I know you all know about this, right? So why do we need protein in our diet? We talk about essential amino acids and nitrogen, right? How would you explain that to somebody on the airplane? You know, why do we need essential amino acids and nitrogen? Or your grandmother? Why is it that, you know, you're telling her she needs to have more protein in her diet? Maybe you're not telling her that. Basic, yeah. Okay. So we need to have those for basic protein synthesis, right? What are all the protein, you know, when we think about proteins, what they do in the body, right? What are all the different ways that we need proteins? I mean, what are the types of proteins we have, categories and things like that? We just talked about enzymes, right? Those are proteins. What else? Sorry? Yeah, muscle fibers, structure, right? Transport, absolutely, right? So, you know, proteins are everywhere. Why do we need non-specifically nitrogen? I mean, obviously nitrogen is part of our amino acids, right? As amino groups and all that. So we need essential amino acids to build proteins, so that's clear. Why do we need nitrogen just as a non-specific kind of thing, not necessarily as part of an essential amino acid? What else in the body? Yeah. Sorry, DNA precursors, excellent, right? So that's one, and there are other compounds that involve nitrogen, but DNA and RNA are a big one. Okay, so when we talk about infants and children, we talk about growth and then maintaining tissues, and in adults we tend to say maintenance only except under certain conditions. What are those conditions? When you need more than maintenance. Okay, what else did I hear over? You say it again, whoever said something over there. When do you need more than just maintenance for health, let's say healthy adults? So I heard what you said, but hold that thought just a moment. Yeah. Okay, all right, so that's where we were over here. Let's talk healthy for just a moment. Ashley. Pregnancy. What more marvelous need for additional protein can you have than building a whole human being, for Pete's sake? I mean, sorry, but it's a pretty cool thing. I mean, yeah, pregnancy. And then lactation. I mean, all of those. What other? Healthy. Let's talk healthy. When else? And we were, we were kind of on this topic a moment ago. Yeah, okay. So exercise and bodybuilding. It's not as much as people think it is, but there's an anabolism. At least you're hoping so, right? When you're trying to do resistance training. Yeah.
Same kind of borders on the unhealthy and healthy, but like recovery from surgery.
Yes. So now let's bring in the clinical implications. Recovery from injury. You talked about sarcopenia. Now this is an interesting concept that we don't have time. That would be like a whole course we could have on about sarcopenia, which is loss of muscle and function as we age, but it's also related to different diseases like cancer, HIV infection, cardiac failure, pulmonary failure. You know, these medical conditions that are associated with degradation of our, loss of lean tissue, loss of muscle, mass and function. So we do have these, those are kind of quasi-clinical because they are related very much to what we deal with in clinical settings. And then what Willie mentioned about, wound healing, recovery from illness. Those we hope, while you require to recover, you need to be in an anabolic state, okay? Your first catabolic, that's what they're getting at, is you end up degrading your protein because you're mounting a response to injury or whatever. And then we would like to have people be in an anabolic state afterwards as they recover. Okay, that was kind of long. I didn't mean to spend that much time on that, but it's useful. What do we need to consider about protein? So first is nitrogen content. Proteins vary in terms of their nitrogen content by what? Why would they vary in their content of nitrogen, would you guess? Got protein A over here and protein B over here. What's gonna be different about proteins that would make the nitrogen content vary? Their source, okay. Yeah. Okay, so and we'll go back to where we started today. What were you going to say? Okay, length and composition. Okay, composition. The amino acid content, right? So different amino acids have different nitrogens content, the number of nitrogens that are involved. So we're going to look at amino acid structure and remember that from biochem. Okay, so how big they are, right? You know, just how many amino acids are in their primary sequence is going to affect it, but then also the nitrogen content of the different amino acids. Now that said, those of you that are MNT, what is the factor that we tend to use to estimate nitrogen content in protein? I hear it. Can somebody say it louder so I don't have to? Thank you, 16. I'm like, where's it coming from? I hear. I don't have my glasses on, so you know I can't see a darn thing. I have to see this one. It's really challenging when you get old. So 16% nitrogen is what we tend to use because most proteins, that's kind of where we end up. If you take kind of the average survey of proteins across, you know, normal diet, we end up with roughly 16% nitrogen, okay? So when we do our calculations clinically, that's what we use. But know that different proteins can have higher than that. And again, back to food companies making supplements and things like that for clinical settings, that'll vary a little bit. I'll show you a label in a second where sometimes when it's got some higher, certain amino acids that have higher nitrogen, it can be bigger than 16, higher than 16. Okay, what else do we need to consider about protein? Essential amino acid content and proportions, there we are. Well, actually, that was not totally related to, I mean, it's somewhat, but not completely related to nitrogen content. So this is how good it is, right, in terms of how you know, do we get the full complement of essential amino acids in the right proportion. And digestibility, and these two things, I'm going to click through, these two things, digestibility and essential amino acid content and proportion, that's defining protein quality. So when we talk about protein quality, you know, it's what kind of amino, you know, do we have essential amino acids that are in the right proportions to really optimize the building of protein from them? And how well does that protein get digested and absorbed? Okay, so that's going to impact protein quality. And then we also have to think about human variability because that is, there are a number of factors that you know, humans vary in terms of that are going to affect their requirements, their ability to digest and absorb. Can you think of any of those factors? What kind of factors are we talking about when we talk about human factors that can influence requirements of for protein and the way we digest and absorb, maybe, or yeah? It is very much an important factor, right? Because, and how do we know that, right? How are the DRIs organized? By age, right? So we know that young, you know, kids, babies need more than kids, we need more than adolescents, and need more than adults, right? So age is very much an important factor. And I think I'm getting a little ahead of myself. I think I have a slide later. Let me just look for a second here. Yeah, I have a slide. So we can talk a little bit more about that in a moment. So let's look at some structures that, did you have to memorize amino acid structures in biochem? Great. No, I'm not going to ask you to write out a bunch of structures, right? We're not going to ask you to do that. However, it is helpful to dredge back to that because it does help us kind of think about the nitrogen content, if you remember. And these, asparagine, glutamine, and I have to admit, glutamine, for all its positives and negatives, has been something that I have thought a lot about clinically. I mean, it's something that's, so it's a good one to remember. It's got 2 nitrogens, right? Asparagine is its close cousin, and that's got 2 nitrogens. Anybody remember this structure? One of those aromatic amino acids. I think you're right. Go ahead, just say it louder. Which one, what do you think it is? Yay, you got it. Tryptophan. Ding, ding, ding. If I had a prize, I would give it to you. So tryptophan. There are not that many that have those phenolic ring structures, but tryptophan is one of them. So it's also got 2 nitrogens. So these are all 2. We've got ones that just have 1. And so this is my, my little quiz of the day. Obviously, I really liked biochemistry. I know that's geeky. You have to admit that, Kind of liked the structures. Although I had to remind myself, so don't feel bad if you don't remember. Anybody know what this one is? This really oddball one? Yeah, who said it? Histidine. I'm not going to click yet because I can't remember which ones I animated first. So this one doesn't look like it really is. I mean, I've got it, the CH2, the methyl groups are, I've got them compacted here. So this is a long chain, I mean, not that long of a chain, but there are 4 of these. Lysine. Anybody remember this one? Arginine. Awesome. Very good. So arginine, I'm going to click through here to give you the labels. Arginine is the most that we have, 3 nitrogens. So you can imagine if you have a protein that has a lot of arginine, maybe it's also got a lot of lysine and, histidine. 4. I'm so sorry. I was spacing. I thought it was more than 3. Histidine has 3. Arginine's got 4. I can't see that. You can see that, right? Can you count them? 1, 2, 3, 4. Okay, it's the only one that's got that many. So arginine has 4 nitrogens, and it makes a protein that's got a lot of arginine in it. Or a formula, if, sometimes we'll give formulas that are enhanced, or, we'll add a little extra arginine. It's not well proven, I'll have to say, but companies will do that. And when they do that, then they're increasing the nitrogen content. Excuse me. All right, wonderful. Okay, and this is also, I know you remember the high biologic value, low biologic value concept. So complete proteins, when we say that, it means it's got the full complement of essential amino acids in the correct proportion, right? And these are usually animal in origin, except gelatin is very poor. It's missing. I can't remember which ones it's missing. But there are important exceptions to this, right? So we have vegetable proteins that are complete. Anybody have any ideas what vegetable proteins are considered complete or high biologic value? Yes, I'm hearing it. Soy, right? Soy's the best example I can think of. I believe quinoa is also thought to be a complete protein. I have not totally looked this up lately, so if anybody know of any others that you've looked at and can throw out there, but quinoa, I think, is one of those that's a grain that is got a complete complement. So that's important to know. But usually you can, if you're going for the easy, low-hanging, bar of trying to get high biologic value, animal proteins tend to be the sure bet. But it's certainly possible with a vegetarian diet to eat soy and other quinoa to get complete protein. When we say low biologic value or incomplete, it means you're lacking one or more of the essential. And the concept of the limiting amino acid, the one that is, or does anyone remember before I give you the definition, what would be the limiting amino acid in a low biologic value protein? Anybody? So it's the amino acid that would be present in the lowest amount, so the one that is kind of limiting the quality of the protein, if you will, or think of it that way, present in the lowest percentage. Typically, and we use, historically we've used egg protein as sort of one of the ways that we evaluate that quality of a protein. I think now we've gone to using the amino acid pattern needed to support growth in a 1 to 3-year-old as the sort of litmus, but it's the same concept. You got this kind of perfect profile, and then you can compare a protein against it. So when we talk about complementary proteins, what's that concept about? Remember that? Yeah. Exactly, right. Yep, that's a very well said, actually. Right? So you're mixing and matching to create a full profile by bringing two proteins that might individually be incomplete, and you want to get group proteins that are not lacking the same amino acid, right? So you want to complement the profiles by bringing together two different kind of proteins. And so this concept of combining proteins, you know, and I give you these examples are probably the most widely cited, right? Legumes are limiting in that sulfur-containing amino acid methionine. They've got plenty of lysine. On the other hand, grains, most grains, wheat, for example, lysine is limiting, and you've got plenty of the methionine, right? So then you bring them together, and you got a perfect protein, or a complete protein. It does not have to be at the same meal, but typically it's thought during the same course of a day or so is adequate. What else do I want to just make sure we're all on the same page? You've heard of different terms for, and actually there are more terms than this. These are the simplified ones. Lacto-ovo, vegetarian. I mean, there are more creative terms out there. And then vegan, right? What's the difference? What do you think of when you think of vegan? No animal products at all, right? And that can extend to medications and all sorts of other lifestyle choices as well in terms of clothing and other products and that kind of thing. I'm looking at my notes because I always have to remind myself, what else do I want to say? Well, while we're talking about this, remember this probably, maybe. Did you learn about why what about corn that can be problematic historically? If you've got a corn-based diet, you remember what the issue is with corn? Yeah. 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 Yep. So corn is limiting in tryptophan too, right? And the niacin that's in there, kind of, you know, we can make some tryptophan from niacin, right? Is that I'm trying to remember all the details myself, but the idea is we treat corn with lime to release that, to allow that niacin to be more available, and that prevents pellagra, right? That's the primary thing. That's the primary thing. Don't worry about the tryptophan. It is limiting in tryptophan, so that's why we combine it with other foods. So many of the cultures that consume corn as a base, like corn, you know, you've got beans or other sources of protein that get mixed together. Okay, great, good memory on that. Plant proteins, and just to, you know, most of the world is consuming plant protein as the primary source of protein, and it's the U.S. That has been traditionally, you know, much lower in terms of our consumption of vegetable protein. Although that's, I hope and think, I do believe that is changing as people are becoming more open to different ways of eating. This is a label that just shows you why this kind of comes up. You know, it comes up clinically. I didn't talk about net protein utilization. That's another concept that you'll see in textbooks about it. But, you know, providing higher biologic value. It'll talk, this label, I don't think I pulled this one, I mean the other part of it, but it probably had something about what percent nitrogen was in the formula as well. So these labels will show these kinds of things. And if you will bear with me, we are almost through with this, and I know you need a break. I haven't forgotten that you need a break. But if we could just kind of scoot through the rest of these little slides, we have 3 or 4 of them, if you can hang with me. I'm bad about that, aren't I? I get little. So what else about protein digestibility? Animal proteins tend to be better absorbed or digested than, not absorbed, digested than plant proteins, and that's because there are factors in many plants, like trypsin inhibitors. What do I want to say about that? Trypsin inhibitors are present in some plants like soybean, and they're inactivated by heating, which is the good news. So, you know, if you steam your edamame instead of eating them raw from the field, you'll inactivate those problematic things that will, you know, if you're inhibiting trypsin, you can imagine that has an impact on whole protein digestion, not just the protein that's in the food you're eating, but it could be problematic. And then fiber, you remember what trypsin does, right? We just talked about that, so I'm going to just have you remember that later. And then fiber and phytates. Phytates combined basically are high in legumes and can bind to proteins, or they can interfere with enzyme accessibility, getting into that primary structure. So that's part of why plant foods, especially, you know, legumes, if we you know, can interfere a little bit with protein digestibility. Cooking does a lot to help break those walls, you know, the plant walls down, and help us get better accessibility. But if you compare it to animal protein, that's why there's a differential. Okay, human factors we talked about. Age was already mentioned. Body size, right? So the larger the person, typically, the higher the protein requirement. Now this is a little bit macro when I talk about that, right? So how are the DRIs? What is the DRI for adults, you know, 18 and over? Anybody? Yeah, 0.8 what? Grams per kilogram body weight, right? So we in a very macro way, we don't, you know, gear it towards body composition or anything. We do the easy way because that's what we've got to work with. So we do it by body weight. So body size definitely affects requirements. Physiologic state, we talked about, you mentioned a moment ago, pregnancy, lactation, right? You know, people that are bodybuilding, people that are in recovery from illness, all of those are physiologic states that will, you know, change your protein requirement from the standard maintenance level. And, you know, this is not on this list, but I'll just say that kind of in combination of these two things, you know, if we think about lean body mass, you know, the amount of muscle that you have on board, to maintain that, you're going to need a little bit, if you've got someone who's highly muscled over here versus, you know, me, you know, that highly muscled person is going to need more protein to maintain that mass. So that's where body weight, you know, we use it as a surrogate for that, but it's not always spot on. And then level of energy intake. So I ask you a question here. Why would energy intake influence protein requirements? Say somebody is, I don't know. Well, I'm not going to think about this for a moment, if you can, before we take a break, if you're just not dying to take a break. I think this is my last slide. It is the last slide. What do you know about this? How could they be related in some way? What happens if you don't take in enough energy? Yeah, beautiful. You've just hit it, right? So you start catabolizing your lean tissue to make what? Glucose for your brain, among other tissues that need it, but brain certainly is a high demander of glucose. So if you don't take in enough energy, you're going to catabolize your protein, your muscle, right? That's a physiologic, you know, it's useful that can happen, but it's not very good to have that happen, right? So, you know, we say protein sparing by providing adequate calories, in the form of carbohydrate, we need a certain amount of carbohydrate to meet the brain's need for glucose. It's not a high amount, but minimum 100 to 150 grams is sort of a general. But we also need adequate energy, right? So we don't break down our protein. So that's what protein sparing means. Have you heard that before? Probably, maybe. And then the last point is the DRI for protein differs for different groups of people. We said 0.8 grams per kilogram is for adults, and that's the main one you should just kind of keep in mind. Incidentally, what do you think about that? If you were to say, okay, I want you to, tomorrow, I want you to eat just 0.8 grams per kilogram protein in the context of a diet, right? How do you think that would feel? Or has anyone ever, do you know what level you tend to eat? Anybody in the room know what gram per kilogram they eat? You want to say? I mean, you don't have to if you don't want to share. Okay. Okay, right. 1.4 gram per kilogram. I mean, that's not that far off from average, but you maybe, you're focusing on it maybe, or I mean, it's not even that much, really. So 0.8 is a fair restriction if you were to eat that. It's actually, so it's the minimum that we need. We don't really, we don't need a lot to maintain. Unless you're, if you're bodybuilding or whatever, that there may be, or you're trying to recover from injury. In the hospital setting, we aim for 1.5 to maybe 2 grams per kilogram to help people get over injury. And maybe a burn patient, we might do even higher than that, right? So we don't need a ton to just maintain unless you've got some other needs. But it's important to know that, because as you tell people, 0.8 grams per kilogram, it's really, it would feel like a pretty significant restriction if you actually ate that level. So just to keep that in mind. All right, I know I've kept you over. So take a break. And how long do we give them? Is 5 okay, or we give them 10? 10 whole minutes? Wow, okay. No, that's okay. 10 minutes. We'll come back. I should have looked at my notes ahead. Do? So it's, and then just hit continue there? Okay. Perfect. Thank you very much. Okay. Whoa. That woke you up. I'll assume that everyone's back. All right, so any questions about what we've talked about so far this morning? Okay, now, you know, and again, you all have had biochemistry, right, mostly. So I do kind of assume that a lot of this will be, especially the first part is, it's a review. And I know in biochem you do talk about urea synthesis and other things like that, but we're going to revisit those things so that they're really solid for you, before you move on with your lives. So I'm back here in this little roadmap. Now we're going to talk about kind of the amino acid pool, and we'll talk about, next what happens to, the nitrogen and the carbon of amino acids and all that. So back to our roadmap here. We'll stay with amino acids for a while. So remember, this is the structure. We got the alpha carboxyl, the alpha amino group. This is the alpha carbon, right? And the other thing that I mentioned a moment ago is the R group, right? That's the functional group. It's what makes each amino acid unique, gives it its particular chemical properties, et cetera. You remember maybe what are some of the attributes of different R groups depending on the amino acid? What kinds of things might be different? What might be we think about as you were memorizing your chemical structures of amino acids? I know you were probably paying attention to the things. Sarah, you got the charge, right? So it could be a negatively charged group, or we'll just say the charge, because actually depending on the pH we'll talk about whether it's a negative or positive. And it could be neutral too, right? So the R group, yeah, what? Okay, so the nitrogen content, certainly when we talk about groups of, amino acids, that might help us think about what are the attributes that we think about for R groups in terms of their qualities or characteristics. Like we talked about, yeah, please. Sorry? Okay, so if they are aromatic rings, and we don't, these are, so the categories, I was thinking that if they were highly aromatic, they would be hydrophobic, would be one way we might describe. It's not just aromatic rings, but often the aromatic rings make them hydrophobic. We can also, on the other hand, have hydrophilic, the ones that are more likely to have hydrogen bonding. We talked about methionine, right? That was one that had, what is that? What's special about methionine? It's R group. Sulfur containing, I'm hearing S, so I'm just going to say it's sulfur, right? They might also have the branched chain, we'll show pictures of those in a minute. They might be straight, anyway, small and large even, right? So they vary in a whole lot of different structural ways that we can kind of think about. So we can categorize amino acids by their R groups, like I just mentioned a moment ago. Hydrophilic, hydrophobic, sulfur-containing, hydroxyl-containing. Thank you so much. We can also categorize them by whether they're essential or non-essential. And the other way of thinking about that is indispensable is the same thing as essential. Did you all learn indispensable or essential? Still essential, okay. That was something that I think people tried to change, and maybe it never went anywhere. So I'll use essential and non-essential as well. The third way is by the fate of their carbon skeleton. We can say that they are, I'll get to this, but it's either glucogenic or ketogenic is the terminology we'll use. And I'll get back to that. So let's first look at, some examples. Alanine is our best example probably of a neutral small amino acid. So I say neutral in the in the context of charge, right? What is alanine an example of? A thing that has no net charge. What's the term for that from biochemistry class? And I know one that begins with Z. Yeah, Zwitterion. I don't know if there's another term for that, but Zwitterion, do you remember that term? Because we got a positive on the alpha amino and a negative on the carboxyl, and that's at the kind of neutral pH. Okay, so when we're mostly going to talk about what they look like in the body, around pH 7 or so, roughly. So alanine is a great example of a Zwitterion, no net charge, and it's a small amino acid. Glutamate at the pH of the body is going to have a net negative charge because of this carboxyl group. Will have a negative charge. It's not protonated at that pH, so it's a negative charge. And then arginine has a net positive charge at neutral pH. So that's an example of positively charged at neutral pH. We're showing them roughly around neutral pH. Incidentally, what is that compound? Anybody know what that compound is, where you've got two amino groups combined or joined by a carbon? Yeah? Urea. Eureka. Sorry. Right, so arginine, when we talk about the urea cycle, the last step of the urea cycle is cleaving urea off of arginine, actually. So that's another little tidbit that we'll think about. Here I'm just showing how glutamate and glutamine are cousins, because glutamine has that extra amino group, and we'll call that the gamma carboxyl. It's got an amino group on that gamma carboxyl group for glutamine. What else do I want to say about glutamine? Incidentally, the other cousin pair, aspartate and aspartamine, over here, those have one less carbon in the chain. But the other thing, or the main thing I like to point out, we're going to talk about the metabolism around glutamate and glutamine. So what we say is glutamate is kind of the primary intracellular, very important amino acid, intracellular hub, if you will, of amino acid metabolism, glutamate. Glutamine is a really important nitrogen carrier between tissues. Had you learned that before? I hope I'm into new territory now. So glutamine, this extra nitrogen, is an important way for us to move nitrogen around the body. I mean, we also have other ways, but it's an important carrier of nitrogen. And then the other thing about glutamine that is just something that it'll come out in a lot of different ways as we talk through tissues, is that glutamine is actually an important amino acid for the intestinal cells. The intestine uses glutamine as one of its primary energy sources. And it's also used by immune cells like macrophages and white blood cells will use it for energy. So glutamine, that's part of the reason that we've had such an interest in it clinically speaking, is that it's used for energy by the intestine and immune cells. All right, so this is that gamma carboxyl group on glutamate that I just mentioned a moment ago. The other thing is that our groups are going to influence the structure and function. We already know that, right? Because of the way that proteins fold up, it's all based on their amino acid composition and their primary structure that allows them to interact with amino acids far away in the actual primary sequence. And it dictates how it does its job, right? So hemoglobin, I love, is the example that it's the way it folds up, it allows it to carry oxygen. And I know you know this, you can't graduate without knowing this, so I'm just going to make sure that we all know this. What mineral is needed to bind oxygen within hemoglobin's structure? Somebody shout it out. Say it louder. Iron, absolutely, thank you. We all know that, right? Okay, you're just being quiet because you Don't want to all jump at once, okay? You need to know that. Okay, and here's another picture of it just so you can see how that works. Heme protein allows it to bind iron, and the way it comes together allows that oxygen to be bound and then offloaded at tissues so that we can deliver oxygen to the tissues, etc. We have talked about ionic interactions between negatively charged amino acids and positively charged amino acids. That's how ionic interactions happen. And again, depending on where those amino acids are in the structure, it's going to allow ionic interactions to stabilize the tertiary and quaternary structures of the protein. Now, I just mentioned that normal, we say normal physiology, that's around pH 7 in the blood, okay? Stomach is a different thing, but in the blood. So in the blood, you're going to, if you've got glutamate, it's going to be in this form over here with this carboxyl proton off, and you've got a negative charge on it, okay? If we drop the pH, then it'll look like this over here with glutamate. So let me just think about, I need to, oh boy, yeah, I forgot. At this point in the lecture, I like to remind you of my favorite, no, it's not my favorite, I really hated it when I was a student, the Henderson-Hasselbalch equation. Do you remember that? Oh. And I'm not going to ask you too much about this, but what do you remember about the pKa? So there are some rules about, so we use pKa for the idea about when protons are going to associate or dissociate, right? And the pKa of a particular group is going to dictate when that happens. That's really my take-home basic, real basic way of explaining this or understanding this. We titrate acids, et cetera, to get the proton to come back on, et cetera. So the rule is that protons will come off, dissociate, when the pH rises above the pKa. Write that down just in case you have not remembered that from biochem. It's not locked in your head, the Henderson-Hasselbalch equation, which probably would allow us to figure this out. Right? So the rule is when protons will dissociate when the pH rises above the pKa. So the pKa for this group is around pH 4. So if the pKa is 4, and I'm saying that we're at neutral pH, we're at around 7, does that make sense then that that's going to dissociate? Are we on the same page? That's the level of understanding of the Henderson-Hasselbalch I need you to remember for this point. So the opposite is true. I won't say that. We'll try to keep it in the same language. When we're above the pKa, the protons come off. The one that's going to dissociate, the one that we're talking about. In this case, this one. What about, so this is just showing aspartate and aspartic acid. Those are cousins and similar rules apply. The same pKa of 4 applies to that gamma carboxyl group for aspartate. And then we have positive amino acids. Positive, this one, so those were acidic. Aspartate and glutamate, those are acidic amino acids because they're negatively charged at neutral pH. On the other hand, the positively charged ones, these are basic. So at pH, so let me tell you what I have to think about this. The pKa of this group is 12.5. 12.5. So at pH 7, what is the charge on arginine? Say it louder, will you? It's positive. It doesn't change, right? It'll retain that positive charge. Does that make sense? 12.57 is below that. So we're never going to, unless you would be dead. So we're never going to see arginine without that positive charge in the body. You can do it in the lab, but you're not going to do it in the body. So lysine is another basic one. I showed you that picture earlier in an earlier slide, and then histidine is also one that will for the most part, maintain positive charge. I might as well tell you, I guess. I'm not sure, I don't think this comes up again, but lysine's pKa is 8.3, so it's above. Histidine is a little more of a toss-up. Its pKa is 6, so it's kind of more in equilibrium at pH 7. Okay. So what happens to a charge on an amino acid if the pH changes? We've just talked about it, right? It could change. Not always. It depends on the pKa of the group, right? So acidic ones are going to lose their charge. So think about that just for a minute, right? If we protonate that gamma carboxyl group, it's going to get it's going to get not a positive charge. It's just going to lose the negative charge, and that will destabilize the protein. If it's in the amino acid, if it's in the primary sequence of a protein and you do that, it's going to change that charge, right? And we're going to disrupt all levels of structure except primary, and I know you know what this is called because we've said it several times this morning, but what is it called again when we do that, when we disrupt those other types of associations and the other types of structure of a protein? Not the peptide bond, but everything else? What do we call that process? Denaturation, right? Okay, so when a protein is denatured, that's what you're disrupting all the weak bonds, the ionic interactions, the van der Waals interactions, the hydrophobic interactions, the hydrogen bonding, the disulfide bonds even can be interrupted, etc. So I don't think I give you this. It's like it's a little bit of a keep hitting the same idea here, but it is kind of food and food science and nutrition. So are there any real world examples you can think of for how we use this in cooking perhaps, or how in real life when you're cooking or eating that these concepts might come up? Yeah, Willie? Mm-hmm. Okay. What do we do to them to denature? Heating them probably mostly is gonna, right? So and then you change the structure and okay, so cooking proteins will denature them. Yeah. Yeah. Yep. Yep. So those that don't know how to do this, that don't cook in the room, marinating if you are eating meat, marinating that lemon juice or vinegar or acid, right? Can denature it. Anybody ever try to make cream of tomato soup the wrong way? My kids, I'm trying to teach them how to make a white sauce and the tomato soup, and you both have to be hot. You got to do something to the milk before you put it in. If you put in cold milk to a tomato soup, you know what happens. It's not a very pretty cream of tomato soup. Okay. Anyway, you get the idea. Yeah, not that you would ever do this unless you're asleep when you're having your tea. If you put lemon in it and then you've already added milk, that would do it as well. And then this is really, again, probably overly simplified things to think about, but important, when you get to the pH of the stomach is 2, right? pH 2, roughly 2 to 3, depending. It's variable a little bit. So you're going to drop the pH. What's going to happen to the acidic amino acids, aspartate and the glutamate? So, and you can look back if you want to your picture of those if you want to, but what's going to happen if once they hit the stomach? What happens to the charge? It's going to not be negative. So think about it, it just goes away. The negative charge goes away. When you drop the pH on an aspartate or glutamate, you're going to associate that proton now, right? So I told you the rule is, I told you in the one way, right? When you rise above the pKa, you're going to dissociate. Well, the opposite is true. You get below the pKa, you're going to associate that proton, and then you lose the charge, okay? This is the level I want you to be able to just think it through. Okay, so you're going to change the charge to where aspartate and glutamate are now not going to have a charge at all. They have no net charge because the alpha amino is going to stay positive and the alpha carboxyl will be negative, but they'll lose the gamma carboxyl charge, and then that's going to destabilize the proteins, right? How do you think that helps? You know how to answer this. So this is so simple, but you know, when you are doing that, you're destabilizing all those ionic interactions. What are you doing for the digestibility of that protein, with the digestive enzymes? Yeah, increasing the access so that then the enzymes can get in there to the primary sequence. That's the whole point of why we cook our food, really, and treat it with, treat it with marinating and other ways that we destabilize the protein. So, I mean, I know that's really basic, but I hope that you can kind of apply it in that way. Okay, now let's move on. How many amino acids are there? 20? The essential number, that's moved over the years, but what did you learn? 9? Yeah, I would say 9. And we've got, so we have essential, non-essential. I've got these other terms here. Just ignore them if you really, it does get a little bit wordy. So essential, non-essential, and then we also have conditionally essential. I mentioned a moment ago that there are under certain conditions, some amino acids become conditionally essential. And an example I gave you, glutamine is considered by many to be maybe one that might be conditionally essential, although we're doing work in that area, and it's a little bit challenging sometimes to figure out exactly when is it most useful to give. But the reason we say that is that the supply in the blood tends to drop. A better example, how about in growth? So for kids, there's an amino acid that becomes conditionally essential that has, that kids tend to need a little bit more of. Anybody remember that from life cycle? Arginine. So arginine is considered conditionally essential for kids. And then if we have preemies, premature infants, they need a little bit of extra cysteine and glycine. These are non-essential normally, but cysteine and glycine are thought to be conditionally essential in prematurity. So just a few examples. Arginine for growth. Okay. Actually, I was going to ask you what acronym you have. So did you learn? You learned the essential amino acids. Did you have a mnemonic that you? I have one that I learned, and it's kind of silly. What did you learn? Does it mean anything? No. Okay. Then it's not a mnemonic. Yeah. Okay. You learned them that way, though. So now I'm going to mess you up because I'm going to give you a mnemonic that I learned to try to remember these amino acids. Some biochem professors, sometimes they have unique ways. This is silly. It's not really all that great, but I learned it, so it's stuck. It's like one of those things. That's why it's a mnemonic. Private T.M. Hill. This was so many years ago, too. So however you've learned them, do you remember them enough to help me with what these are? What does the P stand for? In the back, other people that haven't answered. I know it's. You know this. It's in there. You learned it for, Good. Phenylalanine. All right. That's the first one. How about the V? Give me a V. Which one? Valine. All right. We got 2 T's, so I'll wait to click till you've said them both. The essential ones. So there are other amino acids that begin with T. There are 2 that are essential. Say it louder. Tryptophan, yep. What's the other one? Threonine. Okay, great. Tryptophan and threonine. And threonine is one of those that has a hydroxyl in its R group. and tryptophan's an aromatic. Well, we'll talk about the categories. Phenylalanine is also, these two are aromatic, phenylalanine and tryptophan. What about the M? Yep, methionine, that's got the sulfhydryl group. H, histidine, very good. You see, you know these. Isoleucine, all right. Leucine, oops, now I'm going to do it. What's the other L? Lysine, terrific. You already know these, fantastic. So what makes an essential amino acid essential? How would you explain that? Come on. Yeah. The body can't make it. The R group, right? Perfect. So the R group, you can't make it. So you got to get it from the diet. I have just this point here to highlight, because we'll talk about how we can make a little bit of histidine at the kidney when I get to the kidney. But histidine is considered essential for, and when we talk about essentiality, we mean primarily, when we talk about that, we're talking about we need it in kids and infants, right, to support growth. So that's how we define essentiality. If you pull, there's some work that's going on in this area. We do need histidine for adults as well, and it's thought that it's essential for them too, but we can make it elsewhere. So I'll kind of explain that a little bit. We're going to just say there are 9 essential amino acids, and histidine is one of them. Okay, PKU is something, so that when we talk about amino acids, there are some that come up, some ways that it comes up that I think are worth visiting. So PKU, genetically inherited disorder, and it is a problem with this enzyme, phenylalanine monooxygenase. And a little tip about the way I teach amino acid metabolism, and that every time you see a yellow with purple, if you can see that, it's an enzyme. I've tried to be real consistent with that. So it's an enzyme. And you've got a genetic defect in that enzyme. It's an inborn error. And so it causes the phenylalanine to build up, and its toxic byproduct, phenylpyruvate, that can cause mental retardation if it's not treated early. So it's one of those things that we screen for at birth, and we can treat infants with this by giving a special phenylalanine restricted formula. Has all the essential amino acids except phenylalanine, and then we have some supplemental through breast milk and/or formula, very small amounts, to just provide the absolute requirement for phenylalanine that can be used. But it does very well in terms of treating people with PKU. Under these conditions, tyrosine incidentally becomes conditionally essential. So I didn't give you the whole list of conditionally essential amino acids, but this is essentially a degradation pathway that is blocked by this inborn error in this enzyme, phenylalanine monooxygenase. Okay, other things that we know about amino acids. We've got derived amino acids that are post-translationally changed in a protein structure. So you make a protein, and then when we're finally packaging them, we will change an amino acid in the structure of the protein, like we'll methylate histidine. 3-methylhistidine is an amino acid that is found in the muscle protein actin, not just in muscle, it's also in intestine. But we used to use this as a way of sort of giving us a surrogate for lean tissue. We don't use it anymore because it's not a very sensitive measure of muscle mass. Okay, we've got better methods to use. But once it's made, it's irreversible. It can't be recycled back to histidine, and it goes out in the urine. Okay, so that's how we took advantage of that in the old days to try to get at muscle mass. Proline and lysine can both be hydroxylated. And when you hydroxylate proline and lysine, it's very important to the structure of a protein that we absolutely need to get around, to maintain our skin and our hair, and when we're healing, we need to be able to make this protein. Say it louder. Not keratin. Collagen. Collagen, right? So collagen's structure, I'll show you a picture in a second, is bolstered and absolutely fortified. I mean, this collagen is an immensely strong protein in terms of tensile strength. And it's because of these hydroxylated prolines and lysines that are at sequences in the structure of the protein that allow it to form a double helix structure. And it's really a strong protein. Incidentally, anybody remember this? Not that you've had vitamins and minerals, I know, but you might have heard this somewhere. To hydroxylate proline and lysine, you need a vitamin to make collagen. Vitamin C, where'd you learn that? I'm curious. Do you remember where you learned that? Advanced Human, excellent. Love it. Okay, so we need vitamin C. Don't need mega doses of vitamin C, we just need a little bit of vitamin C, right? Vitamin C is useful in that hydroxylation reaction. Lovely. Okay, and that doesn't show it very well. There's a triple helix structure here with sequential hydroxyproline, a lot of proline and glycine as well that allow it to form that structure. Okay, other things about amino acids. They're used in neurotransmitter and hormone synthesis. So tryptophan, for example, is used to synthesize hormones serotonin and melatonin. Tyrosine gets used to make norepinephrine and epinephrine, which are our catecholamines, the hormones that help us run from the bus as we're about to get run over, or the bear that's chasing us in the woods. I don't know, catecholamines. And glutamate acts as a neurotransmitter itself, but it also gets converted to the neurotransmitter GABA, gamma-aminobutyric acid. We have, and this I know we talked about this in MNT, does anybody remember? Why do MAO inhibitors, people that are on MAO inhibitors have to avoid foods high in tyramine? You remember, Crystal? Yes. Yep. The monoamine oxidase is the enzyme you're talking about. Yep. Wonderful. Do you remember what the major problem is if they eat a lot of foods that have tyramine and they're on this medication that's blocking the breakdown of tyramine? Yep. Yep. So we got a couple of hands there. I've got, you were first, I think. Go ahead. It's a pretty big effect. Do you have a different idea? Yes. Yep. Yep. And you probably are having a panic attack, but it's not just panic. It's hypertensive crisis, right? And I'll show you a slide. It's fantastic. You remember all that. I'm so impressed. Okay. So just point out that tyramine is not tyrosine. It is derived from tyrosine. So it is an amino acid derivative when we're talking about tyramine. And I think I have a slide here that kind of gives this to us. So normally monoamine oxidases will break down tyramine. They also actually work on norepinephrine and epinephrine as well to help detoxify or to break them down to form non-toxic metabolites. So if you're taking a medication that drops that blocks that MAO enzyme, tyramine will get converted to norepinephrine and epinephrine, and it leads to a hypertensive crisis where you will have very high blood pressure, headache, and palpitations. And anybody remember what foods are high in tyramine that we might want to be avoiding or limiting? Yes. Yes, so fermented, cured, aged meats and cheeses, fermented foods like sauerkraut and fermented soy products, tempeh, things like that. And there are others that would be on that list. Wonderful. Okay. So amino acids can be categorized by their R groups, and these are the general categories. Oh, I didn't mention nonpolar, polar. Those are the same things as hydrophobic and hydrophilic. Sulfur containing, hydroxyl group containing, you could add this, right? That's the threonine is one example. I've forgotten the other one at the moment. I'll think of it in a second. Serine, I think. Right? Serine is the other one. Dredge, my own brain is. Second categorization is by essentiality, non-essential, essential, conditionally essential. And then the last is by the fate of their carbon skeleton. And so I mentioned this before. They can either, their carbon skeleton can be glucogenic, ketogenic, or both. And do we finish at 25 after? Is it 35 after? Oh, sorry, don't get excited. We've got 10 more minutes. All right, so I think I will just show you how this sort of, my little diagram here works. I've got blue, I've tried to code this a little bit. So what this, I'm not going to have you memorize this, okay? That's the good news. I really don't want you to memorize this. But you need to know that amino acid carbon is really important. We need it, right? And under certain conditions, we're using it to make glucose, right? You've learned about gluconeogenesis. So most amino acids, are both glucogenic and ketogenic. So let me explain what glucogenic means. Actually, you explain. What do you think glucogenic means? Have any idea? What? Glucogenic. I'm going to break the word down. Hey, yeah, wow, that's really great. Okay. Now, what does that really mean? So, have you heard the term anaplerosis? Yeah, good. I'm glad. What does anaplerosis mean? Yeah, Crystal? Oh, no, that's not Crystal. Sorry, I don't have my glasses on. I'm looking over. Yes. Replenishes the carbon in the citric acid cycle. That would be the way we define anaplerosis, or anaplerotic if you were calling it as an adjective, right? Gives rise to a net increase in carbon to the TCA cycle, which means then we can make glucose from it. That's what glucogenic means. So skeleton can be used to make glucose. So most, but not all, amino acids can be used to make glucose. The so that anaplerosis, giving that rise to an increase in carbon to the TCA cycle. Acetyl-CoA is what? How many carbons is that? I think it's 2, right? So you need to have at least 3 carbon units to call it anaplerotic, right? It's giving to a net rise. So the blue are ketogenic. Okay, so if you look at the lists here, there's only one that is only ketogenic, meaning it does not give rise to a net carbon increase. It cannot be used to make glucose. By that definition. The rest are both. So ketogenic, what does that mean? Just in a ketogenic, so again giving rise to something. Keto is used loosely here for fat. Okay, so that we can make ketones too from it, but it's fat. So we can use the carbon to make fat. Well, we can store almost anything as fat. So they're pretty much. Many of them are both. If you look through all of them, I didn't highlight. They fall in both places. Okay, the only one that is just ketogenic, it's uniquely ketogenic, is leucine. When we get to branch chain, when we get to the muscle, I'll show you how it gets oxidized and what it produces, so that it will make sense to you that it is only yielding 2 carbon units. It does not yield any compound, any 3 carbon unit, so it's not anaplerotic at all. there any questions about that? So that's the level I want you to kind of think about this, that what does glucogenic mean? What does ketogenic mean? Leucine, you got to know, it's the only one that we consider to be uniquely ketogenic. It cannot be used to make glucose from it. It's got a very important fate, though, when we talk about different physiologic states that we'll talk about why it's important and how it gets structured. Okay, we have 5 minutes, and I know that we're limited in time because I only have 2.5 days with you. So I am going to push forward. Are you hanging with me for 5 minutes? We got 6 minutes, actually. 6 whole glorious minutes. Okay. So as you notice, by the way, at the beginning of each of these sections and ending, I've got some objectives and summaries. There is a study guide, too, that we have posted. So I would recommend after today's class, just look through it and then bring questions next time, too, to make sure you're really clear about everything. Okay, so the liver is a big one, and this is probably the main story you've heard. I know a lot of this is repetitious, so I hope I'm not putting you totally to sleep by hitting all of these basic things again. I think I've got some other unique things to talk about in terms of liver, and certainly the way the tissues interact in terms of amino acid metabolism is going to take you beyond where you went in biochem class. So, back to our little map here. We are first, we can talk about of course, the body is, multifaceted and a lot of different tissues. We're going to focus, by the way, on this map. When we talk about amino acid pools and metabolism, we're going to talk about the liver, we're going to talk about the intestines, muscle, kidney, and then we're going to talk about inter-organ interplay with glutamine metabolism because it's pretty interesting. At least I find it interesting. So, okay, but we're going to start with the liver. So back to our, we're eating dietary protein. We've talked about how different factors affect how much we need to eat and then how we deal with the protein and how it gets absorbed, digested and absorbed and all that. We're in the small intestine, so after a meal, those amino acids are going to go to the liver through the portal vein, right? And when we get to the liver, the first thing that I think is worth mentioning about amino acid metabolism is that a good proportion of them are catabolized as soon as they get to the liver, which seems a little silly, perhaps, maybe. So 60% get catabolized when it first pass metabolism at the liver. So the question to ask is why so many? Why would so many have to be catabolized when we get to the liver? Do you have any idea why this might be? We're going to talk about the different reactions and things like that are going on, but why don't we just package them up and tuck them away? Yeah. So it's simpler than that. And really it's that we don't store it like glycogen, right? Glucose we can package up and store it in neat little bundles called glycogen. Amino acids coming in, you're going to use some of them to synthesize proteins at the liver, but the rest of them, you don't really have a storage depot per se. We don't have this kind of massive storage container of amino acids that we can just put away. So we either make proteins or we're going to catabolize them. So that's the primary reason. There are enzymatic reaction, enzyme activity reasons as well. But for now, just the majority of them, really, a big fraction of them are going to get catabolized because we can't store them. We have to use them or catabolize them. I guess the how in a moment we're going to talk about the reactions. But I bet you remember what's the number? If you had to think of a reaction involving an amino acid, what comes to mind? What is the reaction that do you remember? A category. It doesn't have to be a specific one, but what do we do to amino acids in metabolism? Did you learn this in biochem? I bet you must have learned something about this reaction. Yeah. What did you say? So deamination, and that's sort of it's a close number 2 to the number 1, which is transamination. So the first step that happens for most amino acids in their metabolism is transamination, and then a close second is deamination. Okay, and we're going to talk about how that happens. So that's kind of how they get catabolized. That's the first beginnings of how they get catabolized. And then the where is in the cells right around the portal vein. So those are called periportal, P-E-R-I, portal hepatocytes. And we're going to hang there for a while. The first next bit of the next class period, we'll talk a lot about periportal hepatocytes. But just before we move on, let me give you kind of 3 things about the liver amino acid metabolism that I want you to keep in mind. Number 1 is that the liver is the primary site for amino acid uptake after a meal. And that makes sense, right? Because it's the portal vein, it's directly feeding into the liver. So number 1 site for amino acid uptake after a meal. Number 2, the liver is the primary site for essential amino acid catabolism. Primary site for essential amino acid catabolism, except for one particular very special group of amino acids. Does anyone know? It'd be the group of amino acids that the muscle really does some important things with. Leucine is a member of this particular club. Yes, the branched chain amino acids. So they're essential, but they are not catabolized at the liver in any, during that first pass metabolism. So primary site for essential amino acid catabolism except the branched chain amino acids. Third point about the liver is that it regulates availability of the amino acids to the body. Essentially, it's the gatekeeper, if you will. So it's really important in metabolism. And you know this probably by other ways that the liver gets involved. It's pretty important. Okay, I will stop there. You've been very patient. Thank you. Have a good afternoon.